You clicked on this video because you heard an OpenAI model just disproved a famous math conjecture. That is true, but the real stakes here go far beyond a single mathematical proof. We are witnessing a fundamental shift in how artificial intelligence works, moving from simple pattern matching to genuine formal reasoning. By the end of this video, you will understand exactly how modern GPU tensor cores and massive parallelism made this possible and what it means for your career in production-grade development. For decades, the field of discrete geometry was dominated by a problem known as the unit distance conjecture. Proposed by the legendary mathematician Paul Erdős, it suggested a strict limit on how many pairs of points in a set can be exactly 1 unit apart. The conjecture claimed that for a set of n points, the number of unit distances could not exceed a bound roughly proportional to n raised to the power of 1 plus a tiny error term. Mathematicians spent generations trying to prove this, treating it as a fundamental law of geometric arrangement. Then, an internal model at OpenAI stepped in and shattered that belief. This was not a case of the AI guessing the right answer. The model did not simply retrieve a fact from its training data. Instead, it engaged in a massive computational search that would have been impossible for any human or traditional computer to complete. The breakthrough relied on the unique architecture of modern graphics processing units. Specifically, the tensor cores within these GPUs allowed the model to evaluate millions of geometric configurations in parallel. This capability transformed the problem from a sequential search into a high-throughput verification pipeline. Imagine trying to find a specific needle in a haystack. A traditional CPU-based theorem prover would check one straw at a time. It is slow, methodical, and often gets stuck in local minima. The new approach treats the haystack as a fluid. It sprays millions of needles into the mix simultaneously, checking every possible angle at once. This massive parallelism allowed the AI to explore an enormous degree of algebraic realizations within number fields. It constructed extremal point sets that violated the conjectured bound, identifying a strategy that experts had previously deemed unviable. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The result was a human-verified counterexample where point sets contain a number of unit distances proportional to the size of the set raised to the power of 1 plus a small epsilon. Subsequent work by mathematician Will Solwin refined this discovery into an explicit lower bound of n raised to the power of 1.014114. This number is not just a random figure. It represents a concrete violation of the old limit and proves that the AI found a configuration that humans had missed. The shift from pattern matching to formal reasoning is real, but it requires a specific architectural approach. Here is the thing that changes everything about how we build systems. The AI did not generate the final proof autonomously. It produced a candidate configuration that required rigorous human verification and simplification by mathematicians. The model acted as a hypothesis generator, proposing geometric structures that looked promising. A deterministic, parallelized verification engine then acted as the oracle to validate those structures. This hybrid architecture is the key to understanding the new paradigm. The model proposes, and the hardware verifies. The production trade-offs in this scenario favored a semi-autonomous loop. The model's hallucinated geometric structures were filtered through a rigorous constraint solver that ran on GPU-accelerated hardware. This demonstrates that for formal proofs, the cost of false positives is managed by parallel verification rather than model accuracy alone. You do not need a perfect model if you have a perfect verification engine running on thousands of cores. This changes the engineering workflow from generating plausible theorems to generating counterexamples that can be stress-tested at scale. This case study reveals a critical pivot for data engineers and software architects. The new bottleneck is no longer just about data ingestion or model training. The challenge is designing reasoning orchestration systems that can scale formal verification logic across thousands of GPU cores to handle combinatorial explosion. Modern large language models for mathematics are not replacing mathematicians. They are acting as hypothesis generators that require a specialized, high-performance compute substrate to validate. The hardware architecture is effectively a co-author of the proof. The specific hardware configurations and exact inference costs for this breakthrough remain proprietary. We do not know the precise production trade-offs between compute intensity and proof validity in every detail. However, the gap in understanding does not diminish the significance of the result. It highlights that massive parallelism unlocks new discovery spaces that were previously inaccessible. The ability to navigate complex algebraic structures through high-throughput parallel search is now a reality. Consider the implications for your own development work. If you are building systems that require deep logical reasoning, you can no longer rely on sequential processing. You must design for massive parallelism. The future of formal verification lies in the collaboration between probabilistic models and deterministic verification engines. The model suggests the path, and the tensor cores validate the journey. This synergy allows us to tackle problems that were once considered intractable. The disproof of the Erdős unit distance conjecture is a milestone. It marks the moment when artificial intelligence stopped being just a tool for finding patterns and started becoming a tool for formal reasoning. The AI identified a strategy experts had previously deemed unviable. It constructed point sets with n raised to the power of 1214114 unit distances. This is not a minor adjustment. It is a fundamental redefinition of what is possible in discrete geometry. The shift from inference to formal proof is now underway. The implications extend far beyond mathematics. Any domain that relies on combinatorial search or formal verification can benefit from this new approach. The key is to build systems where the AI proposes and the hardware verifies. This semi-autonomous collaboration allows us to manage the complexity of modern problems without sacrificing rigor. The future of software engineering is not about replacing human experts. It is about augmenting their capabilities with massive computational power. We are entering a new era where the hardware architecture plays a central role in discovery. The tensor cores are not just accelerators, they are the foundation of a new way of thinking about problem solving. The combination of probabilistic generation and deterministic verification creates a powerful feedback loop. This loop allows us to explore vast solution spaces and find the needles in the haystack with unprecedented speed and accuracy. The era of semi-autonomous mathematics discovery has begun. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.